Now it's time to calculate how much you would weigh if you stood on the surfaces of some of your mystery solar system planets. In this question, you'll learn what your weight is in newtons, as well as how that value changes on different worlds. As the title of the question says, the thing we're trying to find here is your weight on other worlds. Remember that weight is the action of gravity on your mass, so your weight will depend on both how much mass you have and how strong the planet's gravity is. There is just one value the question gives that we'll be using in this calculation, the acceleration caused by the Earth's gravity. You'll need that to figure out your weight in newtons here on the Earth. In this question, you need to predict which inner planet you would weigh the most on and which one you would weigh the least on. The reason we're picking inner planets is because those are usually the ones with solid surfaces you could stand on. So to make our prediction, let's think about how gravity works. The gravitational pull you feel on a planet's surface depends on both the mass of the planet and the radius. The bigger the mass, the greater the pull. But the bigger the radius, the weaker the pull. Since planets with bigger masses usually also have bigger radii, you might be wondering which is more important, mass or radius. In fact, it turns out that mass is the one that dominates. That's because mass changes much faster than radius. If you double the radius of a planet without changing what it's made of, then the mass goes up 8 times. So in general, bigger planets will have stronger gravity. Note that if two planets have almost the same size, then it's possible for the bigger one to have slightly smaller gravity than the smaller one, if the smaller one is denser. But this only comes up in those rare cases where the two planets are very close in mass. So usually you won't have to worry about this. The question also asks you to compare your weight to that on the Earth. Once again, all you really need to do is compare the masses of your planets to the mass of the Earth, and use that to decide which you would weigh more on. In this case, we're doing two different calculations, so we need two different equations. Note that if you need to use multiple equation sheets to fit all of this in, you're welcome to do that. First, you'll find your weight on Earth. This is pretty easy because we know the acceleration due to gravity on the Earth. So in this case, we can just use Newton's second law of motion to find the force of gravity. This can be written as F equals ma, or W equals mg, where W is the weight, m is your mass in kilograms, and little g is the acceleration due to gravity. Also note that I'm not going to be putting you on a scale to see how honest you're being with your mass. So if you decide to fudge the value a little, that's okay, so long as it looks fairly realistic. This approach won't work for planets in your mystery solar system, since you don't already know the acceleration due to gravity on those worlds. So instead, you'll need to use the full universal law of gravity. F sub g equals capital G, m sub 1, m sub 2, divided by d squared. In this equation, F sub g is the gravitational force, or your weight. Capital G is the universal gravitational constant. M sub 1 is the mass of the planet. M sub 2 is your mass, and d is the distance to the center of the planet. Since we assume you're standing on the planet, the distance will be the planet's radius. Note that capital G is not the same as lowercase g. The only additional value you need to add for your weight on Earth is your own mass. If you have experience with the metric system, you may already know what your mass is in kilograms. If you don't know, then just take your weight in pounds and divide that by 2.2. That gives your mass in kilograms. For the other calculation, you'll also need your mass in kilograms. You also need the gravitational constant, capital G, which is 6.67 times 10 to the minus 11 meters cubed per kilogram second squared. Since this is a universal constant, it will always have this value. Finally, you need a couple of values from your mystery solar system table, the masses and radii of the planets you'll be calculating. Make sure you include the units when you write these down. masses in Earth masses, and radii in Earth radii. When you're calculating your weight on Earth, you don't need to do any unit conversions besides turning your mass into kilograms. Everything else is already set up the way you need it. But when you calculate your weight on other worlds, there are several terms to keep track of, each with its own units. An especially important one here is the gravitational constant. It has units of kilograms, meters, and seconds built right into it. So everything else is going to have some combination of those three. You've already got your mass in kilograms, but you need to convert the planet's mass. We'll assume a planet with a mass of 0.5 Earth masses and convert that to kilograms. As we've already seen, you do this by multiplying by a conversion factor of 6 times 10 to the 24th kilograms divided by 1 Earth mass, giving an answer of 3 times 10 to the 24th kilograms. We also need to change the radius from Earth radii to meters so that it fits with the units in the gravitational constant. Let's assume the planet's radius is 0.8 Earth radii. On the Mystery Solar System sheet, you'll see that 1 Earth radius is 6.4 times 10 to the 6th meters. So we multiply the radius by the conversion factor 6.4 times 10 to the 6th meters divided by 1 Earth radius. That gives us just over 5 times 10 to the 6th meters, which is 5 million meters. Generally, we would prefer you to write big numbers like this using exponents. The calculation for your weight on Earth is now very easy. From the formula we saw earlier, your weight is just your mass times the acceleration due to gravity on Earth. So write your mass in kilograms times 9.8 meters per second squared and give the answer. I'm going to use 80 kilograms as an example mass here, so that gives 784 kilograms meters per second squared. Remember that this is the same as 784 newtons. That's a fairly typical answer here. In general, your weight on Earth is going to be somewhere between a few hundred and a little over 1,000 newtons, so that's what you should be expecting. If you get an answer that seems outside of that range, it probably means that something went wrong with the calculation. For your weight on other worlds, we'll need to write out the entire gravitational force equation with all of the values put into it. It might look a little intimidating, but you just have to work through it piece by piece. Notice that I put in all of the units. It may seem like a pain here, but it's still a good practice to keep track of everything. Let's do this in steps. In the first step, we'll multiply out everything on the top of the equation. Notice that one of the kilograms in the masses was canceled out by the kilograms in the gravitational constant. Next, we'll square the radius. When we square the number, we square the unit as well. Finally, we divide the top by the bottom to get the final answer in kilograms meters per second squared. Again, this is the same as newtons. Notice that even though we had large values with exponents on the top and bottom, when we divided them out, the exponents mostly disappeared. Remember, when you divide numbers with exponents, you can subtract the exponents themselves. This helps you check that you're getting the right answer. Once again, you need to see if your answer makes sense and agrees with your calculations. Did you get the biggest weight on the planet you expected? You should also be checking that the values look reasonable. While your weight changes on planets of different sizes, it shouldn't change all that dramatically. Even on a tiny world like the Earth's moon, which is 80 times smaller in mass than Earth, people weigh about 1/6 what they do on Earth. So you shouldn't be seeing weights that are hundreds or thousands of times greater or smaller than your weight on Earth. In general, even the smallest weights should be tens to a couple of hundred newtons. Even the biggest weights probably won't be more than a few thousand newtons. If you're getting numbers well outside of this range, then something has probably gone wrong in your calculations, and you should go back and check your steps. So say whether or not your calculations match your predictions and seem reasonable. If you realize you had a problem with your prediction, explain what you should have said. While if there's a problem with the calculation, explain how you can tell. And of course, go back and try to correct the values. Remember to ask for help if you're not sure.